Right, okay, so I'm trying to get everything in on camera right now. Okay, the supercapacitors are currently discharging at the moment. Just to make sure I get everything in. Right, the tissue, I can see the LEDs flashing at the moment. So the supercapacitors are currently discharging into the battery. So this is the residual current, which is low, and told us. Yeah, it's coming back now. So now we can see current 100, well, it's 97 milliamps, but that's going straight into the battery right now. Oh, I can't get this meter lined up. Trying to get this meter on the camera better. Ah, the light keeps reflecting on it. Hang on. So to put underneath that. My meter's not level. Can't seem to get anything. Oh, right, now you can't see it at all. Let's see. I think that's working actually. I'm probably going to knock it or something. Oh, I blocked the input current now. You can't see that. Oh, that's the minute. Right, oh dear. Right, that's the supercapacitor hasn't tripped over yet, so the load's gonna come back in a minute on the input. Sorry, the output. That's the input, 410 milliamps. Damn it. Right, there we go. So it's actually dropped to 370 milliamps. 220 milliamps, and it's dropping to. Hang on. I was trying to get this set up, you see. So our loading output is 152 milliamps right now. The output current. Input is still 420 milliamps. 19 volts. This is the RPM. Damn it. Right, I need something to put that rest that on that's a bit better. The vibration's knocking it over. Hang on. This word. Stick that on the back, that should help it from falling over. Right, input, output current 147 milliamps right now. And we're going into the bottom end load, which is about 4 volts right now. 146 milliamps output. This stupid thing. Blue tack. Where's the blue tack? The blue tack should stop this from falling over. Right, that'll work. If I can get the damn angle right. Right, there we go. So I've blocked the input. There's the input current. We're at 410 milliamps. The actual circuit, the way it's pulse drive, it doesn't actually use more current when it slows down. it actually uses a bit less sometimes. You can get this in the right place. Right. So input current down here. Oh shit, you can't see that. There's something in the way. What is it? What's in the way? Is it this thing? Oh, it's this thing that's in the way. Right. 142 milliamps output into actually 3.33 volts right now. That's output current, sorry. Input current 410 milliamps, RPM 3,947. All my LEDs are much more consistent now. They don't flicker like they used to do. It's more stable. Oh damn it, is my audio on? Oh, testing. Yeah, it's on. I need to turn that flipping accelerator thing off. It's probably causing a lot of noise. Right. Our CPU tends to rattle, make a lot of noise when I'm going to try to back this out a bit more if I can. Just get this round here so you can see the input current better. And bend this gooseneck back a bit. That's better. Right, so you can see the oscilloscope. In the background, which is over there, so you can see the waveform on it. LEDs are more consistent, they're not flickering on and off like they used to do. RPM 3,971, input current 410 milliamps, and we're at 19 volts. And notice something interesting. My current limiter has not kicked in. Before it would start to current limit because of increased drag, because it's still set to 550 milliamps on the input, and my current limiting on the yellow LED is not even coming on. So we're doing even better than before. We haven't got the current limiting circuit kicking in. Output is currently 137 milliamps into 3.61 volts, which is up there. I'll see if I can hook up my other meter so we can see the voltage on there. Let me see, have I got room to put that? Yeah, I can put my other meter on here. To get this connected up so we can watch the voltage on the output side, which will be about 1, maybe 2 volts higher because of the voltage drop across the long wire that's going up there. So let me just get this clipped on somewhere without catching my hand in the blooming rotor. Ouch! I'm going to clip it around the back here actually. I'm less likely to catch my hands. So I want the let's see, positive, negative should be there. Oh, it's flipping leads. I think I'm clipped on, right? Am I? Right, yeah. So that's the output voltage that we're going into. That's what the 131 milliamps is going into. Is this voltage here. This thing's moving because of the vibration. It's not vibrating a lot. It's just enough to make it dance a bit. It's a little bit, not much. I'll stick this blue tack down here. Should stop it. Right, so that's the output voltage. and that's the output current. Input current RPM, and we're climbing slowly in output voltage, and as we're charging it we can gauge this because it's dark now outside, the daylight's gone, so we can see that this is moving a lot faster charging than it used to do, which is really good news. Yeah, it's a lot of fun. I'll try and get a better lock on my oscilloscope because it's dancing a bit. I need to get past this fucking camera on it. Right. So we can watch the charge cycle. Yeah, there's about 1 volt difference between this voltage at this down at the bottom and what it is up there because of the voltage drop across that long wire. But it's not that significant. .8 milliamps. I'm just giving you some call outs because just in case you can't see it very well. I mean, who's to say that YouTube might not downgrade my video in the future and it might become unreadable. So output voltage 4.92 RPM, 4082 RPM. Input current is still 410 milliamps. And at 19 volts, let me just switch it to the volts setting. See if I can change it so it alternates. Hang on. If I hold it in. Right. Now it will alternate between volts and amps, so you can see the both readings. You can see the current and the volts now, so it'll alternate, and then you can see the voltage and current at the same time. Well, alternately. So current, voltage, current, voltage. There we go. I actually found that by accident the other day. I didn't know it had that setting. By holding the button in, it will alternate and show you both things. And kind of a cool picture, really. Oh, is it this wire? Yeah, it's this wire that's in the way now. Hang on, I've knocked a wire now. Ah. There. Just want to get that wire out of the way. Oh. Thought it was going to fall off. It's stuck on with blue tack, not much to hold it. These batteries are just running the RPM meter, by the way. So as we make progress with this, things should move a lot faster. You know, we should be able to charge it faster, and the video stream should get shorter, is my hope. Yeah, because hanging around for ages and ages watching everything is kind of boring, you know. Oh dear, so I'm yawning, I'm still half asleep. So as explained earlier, for anyone that's just joined us, my output current is on this meter, and we're currently sending out 107.4 milliamps into 6.82 volts on the supercapacitors, and this voltage will slowly climb as the current will possibly, well, it will slowly drop off slightly as the voltage is increasing. My input current and my input voltage are alternating on this screen down here. Well, I'll probably back to use the thick end. So that's the current on the input, which is 400 milliamps right now at 19 volts. So 18.99 volts on the input voltage to the pulse drive circuit, which I built originally over there, which is probably off. Oh, you can see it. So this is the pulse drive circuit, which drives the power MOSFET, which is driving the coils that are at the bottom, and the actual generator coils are staggered, so the slightly overlapped, and the tail end of the output coils run through my circuit down here, which is using my new toroids that I've just wound over the last few days. And as we can see from the LEDs, that actually it's hard to see them because there's a bit of white out. Let's put a light across it. You can see the LEDs are a constant purple colour, and we're getting a constant output on the LEDs now, instead of them flickering and going out and coming back on, going out, coming back on. Because what used to happen was, it used to rev up a bit, then it used to slow down, it used to rev up a bit, then it used to slow down. It was doing that all the time, whereas now it's constant, which means it's more stable, so we're getting a much more linear output now, and we're getting less drag because the actual consumption has dropped right down because there's less drag. We're actually producing more with less consumption, so that's really good. And as we increase the voltage on the output, the RPM will slowly climb, which you can see on this meter here. I'll try and cast a shadow on that so you can see the LEDs without blocking this meter if I can, because we don't really need to see the generator, do we? Ah, that's better. You can see the LEDs there now. You can see how constant they are. But I've gone and blocked the meter over there now, so you can't see that. I can't win. So anyway, there's the meter on the input, which doesn't really change. It'll probably stay around 400 milliamps. It might go up to 410 or 420 as the speed increases, which it usually does. But we are much more stable. Oh, you can't see that properly now. What the hell? That's better. So that's output voltage. And the oscilloscope's in the background, which is right over there, which you can probably make out, but I'm not going to move it around because there's such a lot of messing about and getting chairs out, and I just don't want to be bothered moving that around all the time. More likely to trip over something if I keep doing that. Yeah. So what we're doing is running a long test, which is when we get up to when this gets to about 14 volts or 15 volts, that'll be the end of the test cycle. So we've got a long time to wait, probably an hour, I don't know. And for some reason, since I put the tissue paper there, this meter's gone darker, and I don't know why. That's better. So as I said, that's output current. If I get this damn thing to stay put, right, that's better. So we're live right now. It's 21:23. It's just gone to 21:24. So if you're lagging, you might be watching this a bit later than that time, you know. And just an interesting thing to show you, if you watch the input current, when I turn this thing off for a second, watch the input current when I turn this off, just for a second, look, it's gone to 0, back on. So the only current that's been drawn from that is for the generator. funny because that tissue paper there, you can actually see the display for the voltage and current a lot better now, because normally it's too bright, so that tissue paper sort of balances the white balance a bit, seems to help show things up a bit better. We're almost at 8 volts already. Wow. It's moving pretty fast. When I'm not, it's like when you're boiling a kettle, if you don't watch it, it seems to boil faster. Almost at 8 volts. 8 volts on the output now. So I put this tissue paper on here to balance the light, that's all. While I'm live streaming, you should be able to scroll the scroll bar back and watch earlier. You should be able to move the slider back to watch the start of the test if you've just joined the stream. I can't monitor the chat unfortunately because it stopped working, the live chat stopped working on my computer, but I don't know. You could also speed it up if you go back to the beginning of the test. You could run it at ×2 speed and see things happening twice as fast. But I'll probably sound like Pinky and Perky, you know. just as a recap, output voltage, RPM, output current, and input current and voltage down there. And there's obviously, and the oscilloscope is right over there, which is quite a long way away, but you should be able to make it out. God, there's this video with birds attacking 5G towers. Birds are attacking 5G towers. Can you believe that?
Hey, they're not done, the birds. They know what's happening.
Holy crap.
Good on them, mate. Yeah. God, they're going for it, aren't they? Like, fuck the 5G.
Wow. Holy crap, that's amazing. I'll have to post that on Facebook. we're at 94.1 milliamps into 8.95 volts DC on the supercapacitors. I mean, before, at about this level, I was about 60 milliamps, so it was around 65 milliamps, and we've actually gained something like 35 milliamps or so, which is really good. You notice that the input current is still 400 milliamps. We haven't changed on the input. Those LEDs are really bright. I'll get my little mirror. I can't move the board because the wires might come out. Also, this coil is I've only just finished winding this and fitting it, and the glue, the plastic glue that I stuck it on with is still a bit soft, like it's still setting. It's actually drying. So this is also a stability test. It should show how stable it is now compared to what it used to be, and we can see how much more stable it is because the current is virtually constant. It just drops slowly, steadily. So instead of it twitching and going up and down all the time like it was doing before, it's much more stable. Alright, input current's gone up to 410 milliamps. It actually seems to do that as it gets faster because it's to do with the timing. The timing on the pulse circuit. As it gets faster, it seems to draw more current because it starts to push back against itself. But I could adjust the timing on it, I suppose, but I'm not going to mess with it right now. I'm just going to leave it.
I just realised how noisy that is. Let me try and move the microphone somewhere else. I want to check it. Right, if I put the microphone over here, it shouldn't be as loud. Sorry about that, I didn't realise how loud it was. Well, I'm going to have to stick the microphone. I don't know where I can put it actually. I'm going to have to get that chair out. Give me a minute. What it is hang on. It's basically picking up the magnetic field. It's picking up the magnetic field, and it's also picking up the resonance through the table. Damn it, where can I put this? Right, that should be a bit, that should be better. Let me just monitor it and see. Yeah, that's a lot better. It's picking up the magnetic field. It's picking up the magnetic field, and it's also picking up the resonance through the table. Oh, damn it, where can I put this? That should be a lot better now, yeah. Right, that should be a bit... Oh yeah, something else I forgot. It's got automatic gain control, so it boosts the volume up as well. I need to sort that out. It's picking up the magnetic field, and it's also picking up the resonance through the table. No, damn it, where can I put this? Hang on, it'll be a lot better now. Yeah. I'll turn off the gain. It's got automatic gain control, so it boosts the volume up as well. I need to sort that out. Right, that should be better. I'll turn off the gain.
Right. Ah, can't hear a damn thing now. Couldn't hear a damn thing with that turned off, the gain control. Right, so yeah, oh well. I'll just put noise suppression back on, okay? Right, noise suppression back on. I should sort it out. Right. Yeah, it's Manicam. It's got a pretty hefty. It's got a pretty hefty gain on it. So yeah, oh well. I'll just put noise suppression back on, okay? Right, noise suppression back on. I should sort it out. Yeah, a lot better. Yeah, it's Manicam. It's got a pretty hefty. Yeah, pretty hefty gain on it. So yeah, no. I'll just put noise suppression back on, okay? Right, anyway, that seems to be better. I was just trying to monitor what's going on it. So, as we can see, the new circuit with the new coils is much more stable. My input current is a lot less. My input voltage is actually 1 volt lower than before. It's at 19 volts instead of 20 volts. And we're also getting more current per volts on the output, so it's actually a huge improvement. The LEDs are on all the time instead of flickering and twitching and blinking, and like William Shatner says, blinking, beeping, flashing lights. Yeah, he hates it when everything's blinking and flashing. So yeah, I do. It's constant now, so we're more stable, and our RPM is a lot higher. It's a lot more stable. It's not revving and slowing down, which is what it was doing before. So it'll be fun when I get the rest of this board built, because this is just half of the circuit board built. I've got 2 more toroids to wind. I've got another 4 triacs to install. I've got more coils to install, and so this is basically cascaded in series parallel. So the circuit is pulsed in a sequential mode. So if I could slow this down in slow motion, what would happen is that would pulse on, and then the other stages would pulse on and pulse on, and it would repeat. It would go back to the beginning, so it would be pulse, 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 for a complete cycle. But this is only working at half a cycle right now, so we're actually not getting the full benefit, but it's working anyway. We just have more to do. And as I say, I'm sorry about all that noise at the beginning. I didn't realise that the microphone was picking up all that vibration. It's just the magnetic field it was close to, and the table tends to resonate, and plus the Minicam has got this built-in amplifier that boosts weak signals, so it was bringing up the background noise up to a higher level, so it was that was causing it to sound louder than it really is, because it isn't that loud really. It isn't that loud, it's just that the signal boost on the microphone was making it sound a lot louder than it was. So we're waiting for this to get to 15 volts to see what the final output from, and it should be around 700 milliamps when we get to the final voltage on this, which is in itself a lot better than it used to be when the capacitors are fully charged. Because originally it was previously on the previous test I was doing, it was around 50 milliamps. I think it was about 53 milliamps previously, and now it's close to 70, which is great progress, yeah. So it's a bit boring, I know, right now, but when it's being live streamed, you could watch it at maybe 10 times speed. You could watch it a lot faster, to watch it progress a lot faster, instead of watching a whole hour and a half or something. You could watch an hour and a half in like maybe 20 minutes. You could speed it up and watch it faster, so you know. And as I said earlier, the tissue paper is there just to bring the contrast down a bit, because if I take the tissue paper out, everything, you can't see the LEDs, look. You are able to see the LEDs properly because of the light, so right. You see what difference that makes. Makes it easy to read that meter down there as well. I'm going to go and make myself another coffee. Anyone want one? Get past the camera. Oh, 11.77, 11.79. Oh, right, we're climbing now. My solar MPPT my solar MPPT was on and it's just turned itself off right now. That's why we're seeing a more rapid climb on the charge circuit, which is why it's going up faster now. Because the MPPT only works when there's sufficient power and it has a timeout on it. So if it doesn't get sufficient sunlight, which it won't because it's dark outside, so if it doesn't get any solar power for about a certain amount of time, it basically turns itself off. So now all the power is going directly into the supercapacitors, which is why it's going faster now, which is great news, because I don't want to be waiting around all friggin' night. Oh, my input current's gone down as well, 390 milliamps. Yay! My input current's dropped to 390 milliamps at 18.99 volts. Yeah! Output current 77.4 milliamps. You see, we're getting to the resonant frequency of 50 Hertz. The closer we get to 50 Hertz, the better it's, the circuit is more tuned, it works better, so we're also gaining some speed as well. Less drag. You can see the RPM's going up quite fast now. (4,945 revolutions per minute). My waveform's looking a bit better now because it's started to tilt forwards at the top and tilt backwards at the bottom, which is the phase shifting, which is what my coils do to offset drag, and that's also getting better. The next set of coils I wound, when I wind them, at some point I'm probably going to wind some longer ones and they're going to be even taller than them, but I'm just going to stick with that particular design for now at the same height, because I haven't got the full set of 4, and I can't really predict how well all 4 will work in consecutively, so I'm going to stick to this current design for now. The coils are actually about 3 millihenry each one, so that's 3 millihenry, that one's 3 millihenry, and there's 100 nanofarad capacitor across each one, and that's my circuit. So ignore the red and blue, it's where it came through the other side. So that's basically my circuit for this board down here. These 2 coils are 1 toroid, so they're actually they're in phase. So there's 2 windings on each toroid, and they're actually together with 100 nanofarad capacitor. Well, that's a 47, but I've changed it to 100 nanofarad. So 100 nanofarad capacitor across that. Yeah, so that's my design. Those are the LEDs. Oh, it slipped down a bit. I might tell you if you haven't seen or if you don't know, my generator is quite capable of running up to a maximum of about 8,000 RPM without any problems, but it doesn't get up that far. But at least it's a nice safe overhead in case it ever does. It usually only does that if I've got no load on it at all, but that's the maximum I've tested it at, because this RPM meter doesn't go any higher than 9,999. So I really don't want to push it, you know. There's no need to go that fast anyway. It just creates some more noise, more vibration, and I don't need all that. So what's important is the ability to generate milliamps or current at lower revolutions, and what's important is to keep the input current down and the input voltage down, which is what we're getting at the moment. But, well, we're making progress on the efficiency, but it's certainly not over unity, not yet anyway. We've got a long way to go, I think, really. More coils to add, you know. It seems to be that for every 2 sets of coils that I add, I gain around an extra 40, maybe 35 milliamps. So I'm not sure if it's capable of actually achieving over unity, because even if I have the full set of coils on there, it might not do that, unless of course I can improve the transformers, which I've designed to make it so it'll run faster with less drag and become more efficient. So that's what the aim is, really, is to try and make the most out of what's already there. Rather than trying to add loads and loads of coils, I just want to make it more efficient and have more phase shift, which is what I'm getting at the moment. I am getting more phase shift, but not a lot of phase shift. So yeah, I mean, it's a progression. So I need to make small steps, baby steps, you know, because you can't do too much all at once, because you can overshoot the mark. So I could make a really big toroid, it might be too big, and it might actually overshoot the mark. So you've got to take baby steps with this sort of thing. But we'll get there, I suppose, eventually. If I don't croak it beforehand, and if 5G doesn't get me, or the coronavirus gets me, you know, you never know. My power supply that's keeping the batteries charged up, that's driving everything, it's still got a fault with it. The current limiting circuit keeps lapsing and cutting out. I have to go over there and reset the power supply every now and then, otherwise these batteries that are driving this circuit would eventually just die on me, and well, we don't want that to happen right now while we're doing this test. So I think I've got a bad silicon transistor. I'm going to have to find out which one it is and pull it out and put a new one in. Just haven't figured out which one it is yet, because it's intermittent. Intermittent transistor faults are the worst frigging things you can imagine to find, you know, because they always work when you're testing them, but they just don't work under certain conditions, and they're just a frigging nuisance. I haven't managed to find it yet. What I'll have to do is connect a test circuit with an LED across each transistor and wait for it to go faulty and see when the LED comes on, and that's probably the only way I'm going to find the fault. It's just a lot of messing about. So I have to basically turn the power supply off, back on again, and it seems to sort it out. It's not a dry joint. I've tested for dry joints. It's definitely a bad silicon transistor. It's just annoying me. The other day I thought I'd found the problem. I thought it was a loose fuse socket. The fuse in the back, in the output. I thought, oh, this is what it is. And I timed it up and it was working fine for about, several hours, and then it started doing it again. I thought, shit, it's not that fuse after all, it's something else. But it is a very old power supply, so nothing lasts forever. Yeah. We've been at 74.6 milliamps on the output for quite a long time now. And having just said that, it drops to 73.8. Sod's law. Oh, it's going back up again. Oh, oh dear. So I am yawning. It must be the buzz that's making me go to sleep again. Can't wait to finish this test so I can turn the damn thing off. As I said, I was hoping to reach about 14 volts. We're not far away now. Maybe 14, yeah. The relay might click though, and it might discharge, so and charge the battery up. I don't know. We'll have to see what happens. If the relay clicks, that's going to be the end of the experiment. We'll know that because the current will drop and the RPM will go up and the output voltage should go up as well. We are very close to the top end now. 12.7 on the other voltage, and this is 13.5. Actually, we've only got 0.7 volts difference now between this one and the one across the room, because higher voltage you get less of a voltage drop across the distance. If you remember when we used to be at this point, at this voltage, we used to have about 56 milliamps. Now we're at 73, so there's a big difference there. Ah. So interesting to find out what the temperature is on the bearings, because they do kind of get warm. That's another reason why I don't like pushing it too fast, but let's have a look. According to this, the bearing temperature is about 24 Celsius, which is about 2 Celsius higher than room temperature, so that's, from a distance, it's hard to tell really, but there's quite a bit of thermal heat inside the generator from the pulse coils, which is 28.4, because it seeps through the plastic some of the heat. So the drive circuit does generate a bit of heat. Now, we'll see what temperature the actual drive coils are. I can't quite get to them. Hard to get to them actually. Well, it's usually around 80 Celsius usually, but it's about 60. So I'll go about 60 degrees Celsius on the drive coils, which are at the bottom. I'll put them at the bottom simply because it's the coolest place to put them really. Let's see if we can get to it on this side. .67 degrees Celsius is what the drive coils are. Pretty warm. Well, they are both. There's two of them. They're actually drawing about 200 milliamps per coil, so they will get warm. Maybe 300 milliamps. Actually, no, 330 milliamps per coil. No, it can't be. We're only consuming 410 milliamps, so yeah. Yeah, that's right. I'm not thinking now. My brain's not working. Right, we're pretty close to 14 volts. I'm going to call it quits in a minute. But you can see that we're at 72.3 milliamps on the output. Normally at this stage, we'd be lucky to have 50 milliamps at this point. Normally, it would be probably 55 at a max, but we've got 72.2 milliamps now, which is really, really significantly better than before. And these LEDs have been constant all the time, steady as a rock, no flickering. And I could trim these trimmers and get more power out, but it would slow down a bit. Actually, that might be worth trying out, because let's just see if I can trim these a little bit better. See if I can get a little bit more juice out of it without actually without drawing more current. That's the main thing. Yeah, we've got 75. Is it slowing down? It is a bit. Right, 78 milliamps, and we're losing a bit of speed. Let's see if we can actually keep that gain. See if it starts to speed up again in a sec. 5,109. Oh yeah, we're gaining again now. And we've actually got an extra 5 milliamps out of it. Oh, but look at the input. The input's gone up to 420 milliamps. So that's not really a gain, because I'm using an extra 10 milliamps on the input. So let's back that out again. A little bit. We're going to have to gain speed again now. We're back to 410 milliamps on the input. So let's just see if it settles. We're at 70 milliamps. Climbing. $71.4. $5,265 RPM climbing still, so yeah, that's not bad. There's still tuning to do. It's interesting, but the very first trimmer on the first coil has more effect than the other subsequent ones. That's obviously because the phase isn't quite out of phase at the start, but it moves out of phase as we go along more and more. So let's try this one. So I like to look a bit of tuning. Yeah, we're not bad. 72 milliamps is pretty good. We're almost at 14 volts anyway, and speed's stabilised. It's important to get the waveform right. That's why I'm looking at the scope as well, because the waveform's got to be balanced evenly. So we're almost at 14 volts. I'm going to call it quits when we get to 14. Just want to get that waveform a little bit more balanced. It's a little bit off. Yeah, that'll do. Right, we're 14 volts, and yeah, I mean, there's the supercapacitors up there say that we're at 13.7. I think that's more than enough for the test, so we're going to turn it off now, and the supercapacitors will probably discharge into the battery, so I'm just going to turn it off and you can see how long it takes to stop, basically. So we're going to end this test. Alright, it's disconnected and it's freewheeling now. And this will start to drop now because power's been consumed at the other end by that meter. Anyway, interesting test. Right from the bottom end all the way up. It takes a long time to stop this thing because there's virtually no drag on it at all. There's very little cogging. Here I should be able to see this wheel just before it stops. You should be able to see the magnets on it. And when it gets to about 40 RPM you might be able to see it. I can just about see it now. 600 RPM. The rotor drums actually weigh about kilogram or something, so there's quite a lot of mass. Anyway, that's the end of the experiment. This will start to drop now. I'm going to discharge them to the battery before the meter up there uses all the juice. So anyway, hope you enjoyed watching the long test. And I'm just glad to get a bit of peace and quiet now, actually. I'm going to discharge the supercapacitor, so this will start to go down, because I'm going to send that power to the battery now. I've got to get past the camera. There we go. So that's going to discharge into the battery now. It's going to charge it. My battery. It'll be about 1.9 amps going into the battery, so it'll move down pretty fast. It usually drops to about 3 volts and then it resets or something. I've got light reflection on it. How do I get that light reflection off here? We're down to 6 volts now. Kind of hard to see it. I know the flipping light's reflecting on it. The relays will click off in a sec. It actually goes through a boost step-up converter, so it boosts any voltage from about 3 volts up to 16 volts, back up to 12 volts, so 12.2 volts to charge the lithium-ion cells. It draws more current as it gets lower, but that's going to click any second because it's at the bottom end there now. So usually when I start charging this thing from the bottom, there we go, it's clicked. Usually when I start charging these, I'm usually start charging them at 3 volts at this point here. Usually that's the bottom end when I start, and that's usually when you see the charge current now at about 153 milliamps when I start out. And it starts out at that level and it climbs up, so just so you've got a bit of background on it. Anyway, the test is finished. We can use this video as a comparison with later improvements and to see how things evolve. I'm just going to get my meter up this lot. So it's useful to record these things. I mean, some people might say, well, it's kind of boring, but what's the point? Well, the point is, unless you document something, you can't have a reference to compare it to. So by recording it, then it gives me a reference point to go back and look at how things used to be and compare them with how things are now. So, well, not now, but in the future I'll be able to refer to the new testers now, and this one will be the past. So obviously it's worthwhile recording it now because I've got a memory, like I said, and I almost certainly will forget what I did before. So anyway, that's the end of the stream. I'm just going to stick the microphone over there because I want to pack things up. I went and did my backing. I don't know how I did it, but I woke up one morning with a bad back. I can only assume that was in some dream state. And I'll be fighting demons or something. Right, so I'm just going to move the camera away. So, thank you for watching, hope you enjoyed it. It might have been boring, but you never know.